Okay, so let's get started again. So to summarize what we learned many things the last hour, but a summary of the concept of a layer. So a layer is a set of related communication functions, so provide services to the layer above it by using the service below. Okay, so if I'm a layer, I provide services up to those who are above me by using the services which I find below me. Okay, so this looks great, right? But how do we do this? How do we really define and group what's known as related communication functions? I mean, what is related and so forth? And what is actually a communication function? And how do we specify these services? Okay, and here, to do this, there is some guidance and through what's known as reference models. So there are two reference models which are of the most important ones, I would say. And one is called the Open System Interconnection Model, or OSI model. It's sometimes called the ISO model also because it's an ISO standard. ISO is a standardization entity. But anyways, the OSI model has 7 layers and is very, very influential in the sense that it's well structured, it has a nice thought out interfaces and so forth. However, it's not used in practice. Okay, so it's a nice thought model on what one could do and should do perhaps, but at least how one could do it like this. The internet reference model, otherwise, it's either 4 or 5 layers, it depends on how you look at it and depends on which book you look at. So it's either 4 or 5. It's something which is empirical, which means basically it just evolved, right? Without a holistic thinking about now we should do a reference model. And it's something which is used heavily in practice. So you know TCP/IP, you perhaps heard of this. That relates then to the internet reference model. And so we will contrast these towards each other. But when thinking about layers and talking about them and so forth, we typically do that from, at least when we first encounter this, we look at the OSI model because it's clean, right? It's well defined and so forth. However, when we want to do things, we have to probably use the internet reference model. And it's messy, right? And it breaks some of the rules and so forth, right? That one should really, according to this model, use. So these reference models are very useful when how to think and how to understand how things work, and also how to engineer things. Now, in practice, these are only models, so they are not strictly 100% actually used in practice. So practical protocols might, bend the rules here and there, right? Okay, but that's just life, I guess. But let's start to talk about these reference models, how they work, and then we can perhaps talk a little bit about how protocols are actually working and how they are sometimes adhering to the reference model and sometimes breaking it. But anyways, so the OSI model, let's start with that. It has 7 layers. So 7 is the top layer and 1 is the bottom layer. And they all have names and numbers. Okay, so sometimes you talk about layer 4, or sometimes you talk about transport layer. And after a while, you have this translation in your head, right? So you can go from one to the other without thinking too much. So what are the purposes of these layers? Well, it's to provide services, right? So if we go from the bottom, the physical layer, its service is to transfer bits over a physical channel. So a physical channel could be like this, okay? So it provides the service of transferring bits over this. Okay. The data link layer provides a service of transfer of what's known as frames, which is a number of bits that are somehow logically tied to each other. So it's a bunch of bits. You can think of this as a data packets, but data packets on the data link layers is also called frames. And it provides the transfer over frames over a single link. So the physical layer can transmit bits. The data link layer uses this service in order to transmit blocks of bits called frames over one link. The network layer provides transfer of packets, blocks of bits over several links. So now I don't have several links, but suppose that we connect this. The network layer provides transfer of packets over multiple links, multiple of these. The transport layer provides service for sending messages from end node to end node, and so from host to host, from a laptop to the web server. Okay. The session layer is in charge of dialogue management and error recovery, and here is basically to we'll see a little bit later what this is, right? Presentation layer is basically conversion between different data representation. So you know, for instance, a picture could be in JPEG or it could be in PNG and so forth. The bits that are represented, these could be in the order, the least significant bit could be here and the most significant bit could be here, or it could be reversed actually, depending on which computer you use, right? But so this one provides a little bit of conversion services for this. And then the application layer here provides services frequently needed by application software, which is running on top of this. So this could be your HTTP or something like that. Okay. Now, so these 7 layers, should we know them? Well, essentially we should know this, but luckily to us, it was realized that top layers here basically could be grouped into one layer. So this is the original 7 layers of the OSI model. However, the top 3 ones are typically bunched together and called the application layer. And the reason for this is that it turned out that the session and presentation layers, so they really didn't do much, right? So they were very thin. So one bunched that together into what's known as the application layer. However, one kept the numbering here, so it's 1, 2, 3, 4, 7. Okay. So there is no 5 and 6 here to the right-hand side, because the 5 and 6 has been merged into layer number 7. Okay. So what do you need to know? Well, I would like you to know the basic services which are provided by these layers. So it's 5 layers in total. You should know what they're called, what their number is, and basically what service they provide. Okay. Yes. So these protocol message structures, remember the protocols talk to each other by exchanging messages. So they follow a typical structure. So a protocol message typically consists of some 2 parts, or sometimes 3 parts. One is a header part, and this provides control information, addresses, sequence numbers, or whatever. It's basically what the protocol needs in order to function. And if the protocol carries data, which it typically does, then that's in the data field, or sometimes also called the payload. So this is what the protocol, the data which the protocol gets from the layer above, which it's supposed to transfer. Okay. So that carries data from the layer above it. Okay. Sometimes there is also a trailer. So this is a typical way a message, protocol message looks like. There is some data, and this data comes from above. There is some header information, which is basically what the protocol needs in order to communicate with its other peer process at the other end. So this is protocol-specific messages that are supposed to be communicated with the other end. and then there could be some trailer here also. Okay. So the idea here is that when I get some data from above, I don't touch it, I just put it here. Okay, and then I add my information. If I'm HTTP, I add HTTP information here in the header. If I'm TCP, I add TCP information here. If I'm IP, I add IP information here. But I don't touch the data from above. And then possibly I put some stuff here at the end. Okay. So to see this in action, let's look at the transmitting node. And okay, so this process we will see now is called encapsulation. So that is the principle that we never touch the data from above. We just encapsulate that into our message. Okay, so the application program has some application data that's supposed to be transmitted to the application program at the other end. Okay, so here we have two end nodes. And node A and B, say. Okay? And the software here needs to transfer some application data back and forth. Okay, so how is this done? Well, the application program uses services of the application layer. So it pushes down, oops. Sorry, we take that more. Okay, so this animation didn't really work. Okay, but the data is pushed down to the application layer. The application layer takes this as payload and then add a header to this. So application layer header AH. Okay, this AH is for that this protocol entity here should be able to communicate with this one. So this is specific to the protocol that we use, but the data is never used to execute this protocol. Okay, so the application layer protocol pushes down this data down to the transport layer. For the transport layer, the application header and the application data is one block. It's data it gets from above. So it never touches that, but adds its header, which is needed for this protocol entity to talk to that protocol entity. It talks by having information here. It never looks at or uses or modifies the header it got from above, because it's data it got from above. It should not care about what that data is, and it should not use that data. That's the principle. So the data we get from above is encapsulated into this message. Okay. So, and this data is then pushed down to the network layer. Okay, and the network layer sees this as data and adds a network header to this. Okay, and this process is then repeated, and then in the data link layer, the data link layer data consists of everything like this. It's never used or touched, but then it puts a header here, and the data link is also typically puts a trailer to this also. Yeah. We could potentially have trailers up here also, but it really doesn't matter. And then the physical layer gets this data, and it basically treats it as bits and then transmit that over the physical channel. Okay. So what happens at the receiving end here? At the receiving node, these bits are then received by the physical layer and transmitted up or pushed up here. The data link layer then inspects the data link header and trailer, and if everything is okay, then it pushes the data up to the network layer, and the network layer then gets the network header and this stuff. The network layer looks at the network header, processes that. If that's okay, then it pushes the data up, which is this. The transport layer looks at the transport header. If everything is okay, pushes it up. Strips it off and pushes it up. The application layer protocol looks at the application header If everything is okay, then it pushes up the application data. So by doing this process, we enable virtual communication of application data here horizontally. This is virtual communication. We also enable virtual application layer messages going back and forth here, and transport layer messages going back and forth here, network layer, and so forth. Right? So this is the virtual communication paths. The physical communication path is down here, over here, and then up here. Right? But this abstraction is very, very useful to us, right? Because when engineering a protocol here at transport layer, we don't need to know over which cable or what data link protocol is used. We don't care, right? As long as we have a service and we use that. We don't care about how that service has been implemented. Okay. So this information here on this slide is probably one of the most important ones that we talk about today. Right? This idea about encapsulation, that you take data from above and you put that in your envelope, right? You don't touch it. You put it in an envelope and you write your addresses or whatever. That's your header. And you push that down, and that's put into a new envelope with new headers and so forth, another header and so forth. And at the receiving end, you open the envelope, take it out. If it's okay, you push it up. You get an envelope from below, you look at that, is it okay? Then you open it up and push it up, right? Okay? Questions? No? Okay, great. So now we know how the protocol stacks works vertically and horizontally, right? So let's concentrate now on the interaction on the horizontal level here, knowing that this is only virtual communication and the actual physical communication actually is provided by the layer below me. Okay, but if we look at a protocol here, then in layer n, okay, n could be 1, 2, 3, 4, possibly 5 and 6, but typically 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 7, right? Okay, in one node interacts with the layer n in the other node. Okay, so this is the horizontal communication. Okay, so protocols talk horizontally, not vertically. Or rather like this. This one never talks to the protocol which is above or below its peer process on the other end. Okay. So communicating entities at the same layer but at different nodes are called peer processes. So this is a process, a computer piece of software which is running. Okay, it's called a process. And this is a process. So these are called peer processes. And they interact by transmitting data back and forth. Okay. So layer n peer processes use a set of rules and conventions called a layer n protocol. And there could be several versions of this one, but one entity is using just one protocol. So maybe it's TCP, or maybe it's HTTP, but it's not HTTP and DNS at the same time. It's either or. Okay, and they communicate by exchanging what's known as protocol data units, or PDUs. Okay, so this entity here talks to this entity by sending data back and forth, and these data blocks are called PDUs. And the PDUs consist of data and header. And the header here belongs to layer n. So it's layer n entity, layer n PDU, and layer n header. Okay. The data is data it received from above. Okay. So it's your payload, something that you're asked to transfer. The data has nothing to do with the protocol itself, the execution of the protocol. The execution of the protocol is determined by the headers. Okay? Right. So communication between peer processes is virtual, right? We know that it's actually, so it's indirect. layer n plus 1 transfers the information by using services of the layer below it, which is layer n. Okay? So n plus 1 uses the services of layer n. Services are available at so-called service access points, or SAPs, which are unique identifiers. Okay, I'm not sure if this is actually correct, so forget about it at the moment. I need to check this out. We'll see an example later on here that clarifies this. So each layer passes data and control information through these service access points. So this is the interface point between two layers. And it does that until it hits the physical layer when it's actually transmitted over a physical channel, right? So data received from the layer above is called a service data unit or payload, and it's called SDU. And SDUs are encapsulated in PDUs. Okay, so unfortunately, when it comes to protocols and communication networks, there is a lot of acronyms. So if you read a text, it's like PDU, SDU, TCP, HTTP, and whatever, right? So after a while, you start to use these as names, and you forget what they actually stand for. But I encourage you actually to learn these acronyms and what the meaning of them, of course, because that will be very helpful. Okay, so let's see this in action. So we have, say, the n plus 1 layer. Okay, then we have an n plus 1 entity. So this is a piece of software running at a node, which is interacting with a piece of software which is on the same layer but at the different nodes. And they interact by transmitting n plus 1 PDUs. Okay, n plus 1 layer, n plus 1 entity, n plus 1 PDUs. And this specifies then, and these PDUs are formatted according to a protocol which resides in layer n plus 1. Okay, these PDUs, this is virtual communication. So the physical communication actually is done by using the services which is provided by the layer below layer n plus 1. And that's through a piece of what should we call it? An interface which is called this service access point. So this, what should we call it? Brown thing here. So this data, the PDU, which goes back and forth here logically, physically goes down like this to layer n. Okay. At layer n, there is a layer n entity which is transmitting PDUs back and forth to its other entity at the other end. Once this PDU goes over this border, it changes name to a service data unit. So from the perspective of layer n, the PDU or the layer above it, it is its payload, its service data unit. Okay. So this is the data which is requested by the layer n plus 1. Okay, so from the perspective of layer n plus 1 tells it, okay, please transmit this data. Okay, and then there is some control information going on here also to figure out, addresses and stuff like that. But the data that should be transmitted is this. Okay, and layer n, what does it do? Well, it encapsulates this information into its protocol data units. Okay, so layer n entity communicates with layer n entity on the other side, exchanging layer n PDUs. A layer n PDU consists of header information, layer n header information, and a service data unit, layer n service data unit. This layer n service data unit is exactly the protocol data unit from the layer above. Okay, so this message is fed down here, changes name to service data unit. It's put into the protocol data unit together with some header, and it's transmitted here. Okay. Questions? go home and stare at this until you figure it out, okay? Because here, there's room for plenty of confusion here. But it's imperative that you understand this. Okay. One thing that really causes a lot of confusion is that these are exactly the same bits. Same thing, just two different names of exactly the same thing. Okay. So there might be questions about this on quizzes and so forth. Okay, so we have a transport layer PDU, which is then the network layer SDU. Okay. And then, of course, these PDUs are transmitted using the services below. So layer N PDU are pushed down to the layer below it and then becomes its service data unit and so forth. So this is, continuously being done. Okay. Pretty important slide, right? So try to figure this one out for yourself. Okay, and then of course this one has a layer above it also. So physical communication goes through these SAPs. Virtual communications go back and forth like this. Okay. Now, when we talked about the big picture, we're going to talk a little bit about how to specify services. What is a service and how can we think about that? And there are many, many, many attributes to service. A service could be reliable, it could be unreliable, it could be this and that, or that and this, right? And so we're going to go through some of them, which are the most important ones, I would say. So one thing a service can be is being connection-oriented or connection-less. Okay, so let's consider a service provided by layer N, okay? So it's provided by layer N, so that means that it's a service which is used by layer N plus 1. So let's assume that we are layer N. It can be connection-oriented, and one example of a connection-oriented protocol is TCP. So a connection-oriented protocol, what it does, it establishes a connection before transmitting user data. Okay, so that's what it does. So before even sending any payloads, that is data I receive from above, I establish a connection with my peer process at the other end. So I start to talk with the other end first to agree on certain things before I start to transmit actual user data. And user data is the service data unit I get from above. Okay, so create a logical connection with the layer between the layer and SAP at both ends. Okay, so so if I'm layer N, I provide a logical connection between this SAP and this SAP by interacting with my friends on the other side. Okay, then once this is done, step one is done, I start to actually accept data from above, okay, which is this service data units from my perspective. And then I transmit them back and forth, back and forth, back and forth until the layer above me tells me, okay, I'm done, or something breaks, right? But in the good, if everything is working as it should be, I will be informed by the layer above me, okay, I'm done, right? You can, I don't have use of you anymore, you can relax, right? And then what I do then is to tear down the connection. So I talk with the other end, with my friend on the other end, to make sure that we don't need to talk anymore, so we can relax now. Which means that we release buffers and allocated resources. Because when creating this connection between, I reserve some memory space and maybe some processing power and so forth in order to establish this connection and maintain it for some time. When this is not needed, everything is then released and it can be used for other purposes. Connectionless, on the other hand, an example of that is IP. It basically does not, well, it doesn't establish a connection before transmitting data. So if I'm IP or a connectionless protocol, I get some data from above with some address information, and I just put it in a packet and then transmit it. I have no idea if there is a receiver even at the other end. Hopefully there is, but I don't know, because I haven't talked to the other end. I just received some data. Okay, fine, I'll send it. Okay. While connection-oriented, I get some request from above with possibly some data. Then I establish a connection before transmitting it. So these are the two differences. Okay, so simply transmit data, okay, service data units, without connecting to the destination or even checking that there is a destination. Okay, so the service type here that I provide above is not dependent on what I get from below necessarily. So TCP, we know that that is connection oriented, but TCP works on top of IP, which is connectionless. Okay, so me being a layer, I can provide a connection oriented service above and below me there could be connectionless or connection oriented services, right? Both are possible. One way to look at this also is that TCP is refining the service provided by IP to the application layer. Okay? Because sometimes you want connection-oriented services. Okay, questions? Okay. If you remember the first lecture, we talked about telephone system and telegraph system. So the telegram service do you think it's connection-oriented or connectionless? Connectionless. Connectionless, exactly. You just transmit the telegram without first knowing that the receiver is even there. Okay? The telephone system, is that connection-oriented or connectionless? You know that, right? If there are two questions, two choices, right? So it's connection-oriented because there you lift the hook and so forth, and the whole thing is established. You can't send data until both ends have lift up their hooks, right? That's connection oriented. Then also we know that the telephone system is circuit switched and the telegraph system is packet switched. This is not related to connection oriented or connectionless. So these are two different things. So I can do a connection-oriented service over a packet-switched network or a circuit-switched network. Both are possible. So TCP is working over a packet-switched network, but it's connection-oriented, right? And we could also have a connectionless service working over a circuit-switched network. That's fine too. Okay, so these are two different things and are often confused. Right. Continue? Questions? Okay, continue. More names. PDU stands for Protocol Data Unit. Okay. Sometimes we use specific names for PDUs. So different layers, application, transport, network, link, and physical. What is the Protocol Data Unit for these? At the lower, the physical layers, they're transmitting bits. So the PDUs here are just bits. It's the smallest thing you can imagine, right? Link layers, their PDUs, protocol data units, are called frames. Network is called packet, transport, segment, application, message. Okay. Message, segment, packet, frame are blocks of bits. Bits are individual bits. Okay. So it's a single bit actually from the physical layer. It transmits single bit, single bit, single bit, single bit, with no interrelationship. Right? We will, however, be sloppy and use the name packet for any block of bits, regardless in which layer we are in. Okay? When it doesn't matter. When it really matters, one can say, okay, we get a message from above and we use segments and so forth. So sometimes we use these names when they are important. If they're not important, we just call them packets, even though the packet is actually the PDU, which is PDU name reserved for the network layer. Okay. Also, an exception to this is that some physical layers, as we will see later on, is actually packet-based. Wi-Fi, for instance, use a physical layer which is packet-based. But again, this is reality, but the model, OSI model, if we look at the OSI model, the physical one just transmits individual bits. Okay. Now, to do services, we could provide a service which is connection-oriented or connectionless. That's one thing. We can also, typically, each protocol layer has a maximum number of bits it can transmit as one chunk. Okay. So when I receive a service data unit from above, typically I impose a limit to how many bits these could be. Okay. So if I'm a layer, I can tell the layer above it, okay, I provide you a service, I can transmit a maximum 1500 bytes at a time to you over a connectionless service, for instance. Or it could be a connection-oriented with 200 bytes or something like that. Now, if the layer below me, so I say, I promise above, I can transmit 1500 bytes for you, no problem. But the layer below me says, okay, I can only transmit 100 byte messages. So what do I do then? Well, my task then is to make sure that I can transmit 1500 byte messages as one entity by using 100 byte messages, because that's the service below me. So I need to do some type of translation here between what I have offered and what I can get from layer below. Okay. So a layer typically impose an upper limit on the size of the data block. Okay. And for many reasons, this is the case, right? So what one can do is to, if a layer n service data unit is too large to be handled by as a single unit by the layer below me. Okay, so I promise to transmit 1500 bytes, but the layer below me is unable to deal with 1500 byte messages. I only do 100 byte messages. What do I need to do? Well, I basically take these 1500 bytes and I split them up in 100 bytes chunks and transmit these individually. And at the receiving end, my buddy there in the same protocol layer has to glue them together before it provides it up to the layer below it. Okay, so how does that work? Well, in node A, that needs to communicate with node B. Node A service data unit is then split up into multiple protocol data units that are transmitted using headers and so forth as individual entities by the service below me. And at the receiving end, all of these are glued together before they are passed out. Okay. So 1500 bytes comes down, I split them up into 15 packets. I transmit these individually. At the receiving end, I wait until I receive these 15 packets, glue them together, and then present them up to the layer above it. To the layer above it, it looks like I just transmitted 1500 bytes as one packet, but actually I didn't. But this information is hidden to the layer above me. Okay. So this is called segmentation and reassembly. Okay. And this segmentation here is transparent to the layer above it. The layer above me has no idea what I've done, right? And doesn't care, frankly, right? Because I promised transmission of 1500 bytes. Questions? Yeah.
Does that have anything to do with sampling that we learned in the previous course?
Sampling, if this has to do with sampling? Yeah. Not really.
Yes.
No. Okay. One can also think of the opposite. A layer may impose a lower limit on the size of the data block. It might not be happy to transmit just a single bit. It needs maybe a byte, right? Or it needs at least 10 bytes to do its job. Who knows, right? So there might be actually also a lower limit to the size of a data block that it can transmit, or rather it could be for efficiency reasons or implementation or some other reason. So what do we do then? For instance, I promise the layer above me, I can transmit single bits for you, no problem. or I can transmit actually packets with 0 bits, if you like. I can do that for you, right? But the layer below me says, no way I'm going to transmit single bits. I can only transmit 10 bits at the time, or 8 bits. 8 bits is my limit, okay? So what do I need to do? Well, I need to take these single bits until I have 8 bits, and then transmit them as one unit, right? Because the layer below me doesn't accept single bits, except only 8 bits, at the least 8 bits. Okay, so this is the inverse of segmentation and reassembly, and that's sometimes called blocking or aggregation and unblocking. So in node A, we take a number of service data units from above, and we put them into a single protocol data unit for transmission. At the receiving end, we take the protocol data unit and we split them into their individual service data units, which are then sent up individually to the layer above it. Okay. So at the sender side, multiple SDUs are blocked into a single PDU. At the receiving end, the SDUs are unblocked from a single PDU. So at the receiving, I get a PDU, which consists of many service data units. So I put them together, I take them apart and send them up individually to the layer above. Okay? And again, this is transparent to the layer above me. It has no idea what I'm doing and doesn't care. Multiplexing, what's that? A layer end service can be shared by multiple entities above. So if I'm a protocol entity here, I can have several entities that I serve at the same time from above. Okay. So if I'm IP, for instance, I might have if I'm TCP, for instance, I might have HTTP here, DNS here, and maybe a third protocol above, and all of them are communicating through me because they're going to the same destination. Right? So a layer end service can be shared by multiple entities above it, and this is called multiplexing. And for this to work then, we need some special information here. Okay, so suppose we have an entity here, let's call it HTTP, for instance, and here we have maybe DNS. And for some reason, they want to communicate to the same node at the other end. So here is TCP, for instance. So if I'm TCP, I can get messages from an HTTP protocol or messages from a DNS protocol here. They have different syntax and so forth. But for me, it doesn't matter because I treat them as service data units. These are payloads that needs to go over the channel, right? So I encapsulate these service data unit, the blue one and the purple one, into protocol data units, and just happens to transmit the blue one first and the purple one later on. Okay, so here's the data I got from maybe HTTP. It goes like this, ends up in a protocol data unit. I put some network, put some header on top of this, and here as part of the header, it tells the receiving end, okay, so this belongs to the blue protocol at the receiving end. So it knows when receiving this protocol data unit, this entity here goes in and see, okay, so this was an HTTP packet, and transmit that up to the HTTP protocol here, because DNS would not understand it, right? It needs to go to the right one. So here there is a tag or address, if you like, for the receiving end to figure out, is this an HTTP service data unit or a DNS service data unit? Okay. The same thing here. If this is DNS, comes here, it's a DNS message here. The entity at the receiving end looks at the tag here and says, okay, so this should go to DNS, and sends it up through the right service access point here. Okay, so this is multiplexing. Questions? No. Let's see. Okay, let's do one more before the break. Splitting is the inverse of multiplexing. So a layer n+1 entity may use several multiple layer n services. Okay, and this could be useful. For instance, if I'm a protocol layer at n+1, and I would like to provide a very high data rate service to the layer above me, but below me I have several possible transmission paths, but all of them have limited data rates. Okay. So what I can do then is I can send over these in parallel in order to create a higher data rate for the service above me. Okay. So the idea here is that the entity here actually connects to several parallel protocols, or they could be the same protocols, but they are two different entities running in parallel. So I don't know, for instance, yeah, okay. Anyway, so this one needs to transmit data here, and it can do that by sending service data units over one path and the other path. But these service data units then are feeding the same service above here. Okay. Again, if I'm n+1, I'm providing a service above. So I get service data units from above, and then I split them up into two pipes, one which goes the blue path and one which goes the purple path. At the receiving end, I get these, and I still send them up to the same protocol above me. And by doing this, we can increase data rate, because data rate might be limited in these protocols. So maybe this is 1 megabit per second, this is 1 megabit per second, then I can provide 2 megabits per second to the service above. Or it could be like this: I want to be really safe, so I send the same data unit here and here, just to get some redundancy in my transmission. Okay. But anyways, by using several entities below, that's called splitting or inverse multiplexing. Multiplexing was that I served several entities above. Okay, so that's multiplexing. Splitting is I use several entities below. Okay, so that was a lot of words. So let's take 15 minutes. So maybe we convene 5 after the hour.